I now want to talk about a line. When we're dealing with linear algebra, if we have a solution with a single free variable, that is a line. So let's look at a little more in depth on this. Let's start with a line that passes through the origin. This can be seen as starting with a vector and looking at all of the scalar multiples of it, since every vector starts at the origin. Therefore, these are of the form t times our vector v, where t can range over all the real numbers. Next, let's consider a general line. We know that a line is completely determined by 2 points, so we're going to call these 2 points u and v. In this case, our line is described by t of u plus 1 minus t of v, where once again t ranges over all the real numbers. And we can simplify this as well. We can write it as the vector u plus t times u minus v. So let's look at how we can use this in different types of problems. Let's suppose I want to find an equation of the line passing through 4, -3, and 6, 1. We need one of these vectors to be u and one to be v. We'll let the first one be u and the second one be v. The formula then said u plus t times u minus v, so now we can just stick in the information that we have. That gives us 4, -3 plus t times 4, -3 minus 6, 1. We can then subtract. We get 4, 3 plus t times 2, -4. Writing this in terms that look more familiar, we would have the vector 4, 3 plus t times the vector 2, -4. So this is going to look a lot like a solution with one free variable. In this case, t would be our free variable. My next problem, does this line given by 1491 plus t times 426 pass through the origin? This is equivalent to asking if there's a value of t such that 0, 0 is equal to 1491 plus t times 426. And this is actually going to give us two equations, one for the first coordinate, one for the second. The first coordinates would give us 0 is equal to 14 plus 4t, and the second coordinates would give us 0 equal to 91 plus 26t. If we solve the first equation, we get that t is equal to -7/2. The second equation will also give us t equal to -7/2. And so, since these are the same, then yes, it does pass through the origin. If we let t be equal to -7/2, we will get 0, 0. Our next question, is the point 4, 3 on this line given by 2, -5 plus t times -7, 18? This one is going to be very similar to the last one. We have 4, 3 is equal to 2, -5 plus t -7, 18, and we want to know, does this value of t exist? The first components here give us the equation 4 equal to 2 minus 7t. And if we were to solve that, we get t equal to -2/7. The second equation, 3 equal to -5 plus 18t. Solving that gives us t equal to 4/9. And since it's impossible for t to be both -2/7 and 4/9 at the same time, this point is not on the line. I now want to know, do the lines 1, 4, -2 plus t times 3, -2, 5, and 3, -7, 9 plus t times 4, 7, -1 intersect? Based on our last two examples, it's common to want to just set these equations equal to each other and see if we can solve it. But that's actually not what we need to do. There's no reason that the value of t for the first line needs to be the same value of t for the second line. Therefore, what we really need to do is do 1, 4, -2 plus t times 3, -2, 5 is equal to 3, -7, 9 plus s times 4, 7, -1. And now we need to see if this has a solution. Getting our variables on one side and moving to column notation gives us this here, t times 3, -2, 5, plus s times -4, -7, 1 is equal to 2, -11, 11. It's much easier to now see that this is going to be a system of equations, so we can move to an augmented matrix. So here is our augmented matrix, and we need to reduce this to see if it has a solution. Using row operations then gives us 1, 0, 0, 2, 0, 1, 1, 1, or 0, 0, 0. So this does have a solution. T equal to 2 and S equal to 1. That tells us these lines do intersect. And in fact, we can figure out what point they intersect at. Let T be equal to 2 or S equal to 1, and you'll get the same point. The point 7, 0, 8. Let's consider two generic lines, U plus TV and W plus SV. Whenever we're trying to look if these lines intersect or not, there are a few easy ways to do that. The first way, if these lines are the same if and only if U minus W and V are both multiples of our vector Z. So if both of those things are true, this is going to be the same two lines. We can say these two lines are parallel and distinct if and only if V is a multiple of my vector Z, but U minus W is not a multiple of this vector Z. And finally, we can say these two lines intersect if U minus W is in the span of my vectors Z and V.